In my last video segment, I asked you to toss your keys toward the ceiling. So if you sit in a chair, toss an object so it goes straight up and almost hits the ceiling and turns around and comes back down. That leads to a few questions. Number one, when is the object in free fall? Is it while it's in your hand and you begin throwing it upward? Is it while it's traveling upward? Or is it only while it's coming back down? So some people hear the word fall in the term free fall and assume that an object has to be moving downward to be in free fall. But the answer is, as soon as the object left your hand and the only appreciable force acting on the ball or the keys or the pencil or whatever you tossed, as soon as the only force acting on it is gravity, at that point it's in free fall. So while it's rising, it's in free fall. For the split second that it's at the very top, it's in free fall. And as it comes back down, it's in free fall. As soon as it hits your hand, it's no longer in free fall because your hand exerts a force other than the force of gravity. So remember, the definition of free fall is the motion that results when the one and only force acting on an object is gravity. And often we compare motion through the air with free fall as long as the air resistance is negligible in comparison to the weight of the object. Here's another question. When is the speed of the object equal to 0? I think most people get this question right. You'd say right at the very top. Some would say once it hits your hands because it brings it back to rest. And also, okay, but remember, in your hand is no longer free fall. So in what portion of the free fall motion is the velocity 0? And yeah, maybe we'd say while the object is rising, the velocity is positive. And then while the object is falling back down, the velocity is negative. Although that's kind of arbitrary. Your frame of reference is entirely up to you. So you can make a dashed line and say this is the place where position equals 0. And if you choose, you could say downward velocities are positive and upward are negative, just as long as you identify in your motion diagram what you're considering to be forward motion and backward motion. So there's no right or wrong when it comes to assigning positive or negative, as long as you don't do something silly and say both up and down are both positive. That can't possibly be the case. So let's go with the original inclination and say that up is positive and down is negative. And so certainly if the object has positive velocity that's getting less and less and less, and eventually gets some negative velocity, then for a moment, at a single instant in time, it has to have a velocity of 0 at the very top. Which leads me to my third question, question number 3. When is the acceleration equal to 0? And again, some people would say, well, right when it gets to the very top. But be careful. Make sure you understand the difference between velocity and acceleration. It turns out that the acceleration of the object, let me draw this again, it's kind of messy. If an object is thrown upward, turns around and comes almost straight back down, when the object is right here, the acceleration is equal to, well, let me draw my frame of reference before I can tell you what the acceleration is. Let's say position is 0 at this point, up is positive, and down is negative. Oh, well then I know the acceleration right here. It's negative 9.8 meters per second squared. Now why negative? Because gravity pulls in the downward direction, and from this frame of reference, I've decided that downward motion is associated with negative. When the object is right here, what's the acceleration? Well, the velocity is getting less and less, but the acceleration remains constant. Gravity provides a uniform acceleration. So again, at this position, the acceleration is negative 9.8 meters per second squared. What's the acceleration of the object just before it returns to your hand? Well, It's accelerating in the downward direction. That's the pull of gravity, and it's negative 9.8 meters per second squared. In fact, at every single point, even at the highest point, the acceleration is negative 9.8 meters per second squared. So gravity doesn't suddenly disappear, right? The Earth's desire to pull on things does not go away just because your keys happen to reach the highest point of your toss. After all, you didn't start to levitate out of your seat at the moment your keys almost hit the ceiling. So the gravity's acceleration is always negative 9.8 meters per second squared with this frame of reference. Now, had you chosen to make the frame of reference such that down is the positive direction and up is the negative direction, then we'd say that the acceleration at all points is positive 9.8 meters per second squared. And that's perfectly fine, just as long as it matches with your frame of reference and you remain consistent. So I think a common misconception is that while the object is rising, its acceleration is negative, and while it's falling, its acceleration is positive, because some people think positive and negative signs have to do with increasing or decreasing in speed. So while the object is rising, it's slowing down, so its acceleration must be negative. And while the object is falling, it's speeding up, so its acceleration must be positive. So some people think the acceleration changes from negative on the way up to positive on the way down, and therefore must be equal to 0 when it's at the very top. But that's absolutely incorrect. With this chosen frame of reference, the acceleration would always be positive, whether it's rising or falling. And if we go back to our original frame of reference, if you like to think of up as positive and down as negative, then all of these change to negative. And even at the very top, it's negative 9.8. Okay? And we can show this with a graph of motion. So let's make 3 different graphs. We're going to make graphs of acceleration versus time, velocity versus time, and position versus time. So let me draw in all 3 axes, or all 3 sets of axes, I guess I should say. And let's say time goes on the horizontal axis. And so in our first diagram, we'll put acceleration versus time. Then we'll do velocity versus time. And the last one, vertical position versus time. And in each one, we'll indicate that moment in time when the object reaches the highest point. So, of course, here is t equals 0 at the origin. And then that moment in time is when the object reaches the greatest vertical position. Well, the acceleration at all instants in time is always the same steady value. So the graph of the acceleration versus time is very easy. It just has a consistent value of negative 9.8, and the implied units, of course, are meters per second squared. And again, I'm sticking with this frame of reference. Down is negative, up is positive. I won't change my mind anymore. So what about the velocity as a function of time? Well, when the object first came out of your hand, it was moving in the upward direction. And it comes out of your hand traveling as fast as it goes. So it starts out with some large positive initial velocity. And gravity makes that velocity become less and less and less and less until it momentarily reaches 0. And then the object turns around and starts going back in the other direction and has negative velocity. So the velocity is all positive here. The velocity is all negative here, so this is on the way up, this is on the way down, and for one instant in time, the velocity is equal to 0. Now notice, if you were to calculate the slope of this line at any point, so how's the slope right there compared to the slope right here, compared to the slope right, it has the same slope at all points. And isn't that a negative value for the slope? And isn't the slope not only a continuous negative value at all those points identified, but the slope is also of the same value even at that point? Well, remember that the slope on a graph of velocity versus time is an indication of acceleration. And because this has a continuous slope at all points of negative 9.8, now think about it, the units for velocity are in meters per second. So slope is rise over run. So the rise is measured in units of meters per second. The run, as it were, is measured in seconds. So our slope is negative 9.8 meters per second per second. Now, I let you get away with calling that meters per second squared if you prefer, but meters per second might be a more intuitive way of describing the units for acceleration. Okay, so lastly, this brings us to position. Well, we know halfway through the motion is when the position had its greatest overall value. And when you first released it from your hand, it was at the origin. When it returns to your hand, it's back at the origin. And this graph produces a curve. And by the way, the concavity remains constant on this one. In other words, if I want to know the velocity of the object, then I can look at the slope of this graph, right? You recall that. The slope of a graph of position versus time is an indication of velocity. So at this point, for example, there's a fairly large positive slope, which means at this point, there's a reasonable amount of positive velocity. Here, the slope is positive, but it's not as great in value, which means at this point in time, the velocity is still positive, but it's just not as great in value, and so on. But right at this point, you notice the slope of a tangent line is equal to 0. So at that moment, the velocity is 0. But the curve is still concave down even at that point, which is an indication, once again, that the acceleration doesn't equal 0 at that point in time. So the acceleration, we notice, is never equal to 0. It's always negative 9.8 meters per second squared.